Okay, so now I will try. Okay, perfect. We've got this. Okay, well, this is me for all of you who don't know me yet, or this was how I used to look some 20 years ago before I started working in the IT business. Okay, important lesson here, follow me here on Instagram, because there's lots of additional information on RISC-V there. So, well, now, first of all, to start generally on a high level, what the whole RISC-V affair is about. And this question, by the way, is not a joke. I regularly get this in consulting sessions. Who of you already has done anything with RISC-V? Okay, who of you has ever been worried about the excessive dominance of ARM over the microcontroller market? I see some hands, this is good. Okay, well, RISC-V essentially, it's an open source instruction set. This button will kill me. It's an open source instruction set which was developed by the University of Berkeley. And as you see here, it is a completely free instruction set. So this means there are no patents, no licenses, no nothing, even if you have the actual chip in your hand and you put it onto your PCB. Okay, very important, first things first, RISC-V is basically, it's a name for a whole family of different products and processors. So if we have a RISC-V chip, this guy here, and then I go to Macau and I grab one here, then I go to Moscow and I grab one here from a different vendor, it is very, very likely that these are not compatible with one another. And the reason for this is that we are actually looking at two completely different groups. We've got the base ISA up here, which is the actual CPU, and we've got one or more extension ISAs. So it's basically like if you're sitting in first class, you order a steak, and then you tell the stewardess to also bring carrots, potato mash, and a bottle of vodka. And what's also important, all of the crap is versioned. So in many cases, you've also got multiple different versions. Why am I telling you all this? I'm telling you all this so that you can later make a good decision about which RISC-V chip to use. And yes, this book over there, if you use RISC-V seriously, you should try to get it. I don't say buy it, I say get it. Okay, now, looking at the RISC base, the most important thing is a RISC-V chip always is at least 32 bits in word length. There is no 16-bit RISC-V. There will never be a 16-bit RISC-V. Instead, what is available, you see here, is 32-bit. Then there is also 64 and 128-bit. But in practice, especially for our needs in microcontroller space, it's basically going to be one of these two guys. And yes, as for the extensions, there's 50,000 of them. It's literal 50,000 of them, as you can see here. And of course, what is important about this is, I need a clock. What is important about this is that you also need to keep in mind when you are switching from core to core that you need to get the correct versions of these as well. So, any questions so far? Okay, very good. Then let us ask ourselves about learning assembler. In principle, if you ever, any one of you ever did assembly on an 8-bit chip? Which chip? PIC16, AVR? Okay, I'm the only one who did PIC16. That's why I look so old. And, well, generally, the RISC-V architecture is pretty simple to understand, and it's a pretty interesting. They made a few interesting magic, for example, with the 0 register. But in practice, you don't really need to do it because the compiler does it for you anyways. And there is a document which is called the green card. This is very important. It's normally part of Hennessy and Pedersen of the book we had before, but at this URL, you can also find it for free. So, and now I have a little question. Who of you ever did some heavy microcontroller work? Okay, so you use SPI, you use I2C, you use all these peripheral units. And so we've got the famous Is Hess More? Who of you still knows the band? Hess is more, come on, you must know it. Either way, the problem is these peripheral intellectual properties, they are a completely different pair of socks. And they are not part of the RISC-V specification. So if you want to make a RISC-V microcontroller, not only do you need this stuff, but you also need to get the peripheral IP from somewhere. And this is the very big problem. And we're now going to look at it. You see here, we say the chips are not communal. So you need to be very careful. If you have, for example, a C5 RISC-V microcontroller, and C5 decides to end their sectarian existence, then when you switch to GigaDevice, you have to rewrite a lot of the code. It's basically almost as bad a rewrite as switching, say, from SGS Thompson to Microchip or something like that. And yes, this up here is mainly for the managers, because quite regularly I get questions from people, why do the chips cost money? They are open source. Honestly, this is the most common question I get. I am not joking. I'm not joking with you. On my little live stream, that looks good enough. And as I said, this is not a stupid joke. And the interesting thing is, who of you thinks that a RISC-V chip, because there is no licensing fee, always has to be cheaper than an ARM chip? Who thinks this? Okay, I'm happy you people all know the semiconductor market. The economies of scale, together with ARM pissing their pants so much, has led to the weird situation that in some cases you can get ARM chips for cheaper in the end than the RISC-V chips. This is very rare. Now in the chip crisis it's basically impossible, but I'm just mentioning this just in case. And yes, finally, before we go into the actual application, who of you ever worked in a sanction critical environment? Okay, in case you ever work in a sanction-critical environment, which is a place where you can make a lot of money, I'm giving you a bit of a nitty-gritty here. This is about American sanctions. Russian and North Korean sanctions and Persian sanctions work a bit different. This is the American sanction system. We have here a value chain. You see this? And the American just looks at the whole value chain. You at the bottom, the instruction set vendor at the top, and then he just takes any of them and fucks with them. Any one of these four. This is very important. And also, secondarily, if any of these steps use US dollars, they also go after you. This is also very important. So if two Chinese people, if I fly to Macau, I visit my former lab gypsy, I buy 5 chips, and she says, hey Tam, I want $10, and I give her $10, then even though she is a Chinese citizen, I'm an Austrian citizen, we are in Macau, we are still in breach of US sanction regulations. This is very, very important, and you need to keep it in mind. And the solution for all of these problems is GigaDevice. Who of you has ever heard of GigaDevice before? No. Okay. Most RISC-V companies, I'll be honest, are sectarians. It's some fly-by-night sectarian bullshit. This is my personal opinion. I don't work for GigaDevice. I just like their products. GigaDevice, on the other hand, is in the market since 2005. They actually produce NOR flash, and the microcontrollers, for them, it's basically just a hobby. And here we see the whole product portfolio for the VF103. You see that we've got different sizes of memory from 16K to 128K, and we've also got different chip sizes. These, for example, you can solder very easily by hand, these two. And you see here, these are communal. So if you start here, for example, and you see you need more flash, you can simply jump up. And yes, of course, you see here, maximum frequency is 108 megahertz. Does this look similar to any other controller family? STM32F1, anyone? It is, let's put it this way, it is definitely not a clone, this should be obvious. It's a different chip, it's a different architecture. But if you currently know a lot about STM32, this definitely is a way to make your intellectual property more open source, more sanction-proof, and also more available. Because almost all of these SKUs are permanently available on the market. And yes, as I already said, the peripheral design of the two chips is highly similar. The transition is very easy. And there is a very wide ecosystem. Who of you has ever paid a lot of money for embedded development software? I see somebody closing his eyes.
I only used ESP32.
Yeah, but then you are lucky. Then you're on the lucky side. You never had the pleasure of paying $5,000 for your compiler, and another $2 or $3,000 for some other bullshit, and another $2,000 for the debugger probe. It adds up quickly. In the case of RISC-V on Giga device, we've got two options. First of all, we've got Nuclei Studio. On my YouTube channel, you've got 50 videos explaining how to get started. It's a free, open source, Eclipse-based IDE. And if you really do need commercial support, YAR is available. But, you know, YAR the pirate. You know, YAR the pirate. And, you know, if you want to travel on a pirate ship, either you need to be a girl with, well, you know what? Or you need to be a tall guy who knows how to snipe. Or you need to bring a lot of money. So keep that in mind. And the second thing is why I'm suggesting these open source chips. Wide availability. We are very close to Poland. Transfer Multisort Electronic has these chips. And of course the usual Chinese suspects. And when it comes to the actual development boards, we've got these two options here. Before we look at them, does any one of you have any specific questions so far? Any feedback? Oh, okay. That's good. You see here, we've got the two different evaluation board options, which make it easy for you to start immediately. On the bottom, we've got the small start. This chip, this board, the white one, costs about $15 to $20. It has an Arduino-like pinout. And you see here, you've got these mini USB cables. There's one for the programming device, and then there's one for USB OTG. So you can even directly plug in your USB OTG hardware if you want to use it. The big guy up here usually is about $150, $170, and it has all kinds of integrated peripherals. I mean, it's a question of taste as much as a question of need, to quote Neil Tennant. Thank you to the photographers. And I personally, I'll be honest, I prefer these at the bottom for a simple reason. Because these at the bottom, in my company, I'll be honest, we are hardware first. We are a good hardware design team, and we can code. We don't like to code, we can code. And for us, normally, we have at least a basic hardware working very early. So usually I use these boards and then our own custom hardware. If you are more of a software house, by all means, use the blue one. Okay, and now I still want to, we still have a bit of time, I still want to very quickly show you the project structure of a nuclei generated project. We see over here these includes. This is very important because these files here, they contain the actual drivers for the individual units, individual function units for the DAC and so on and so on. And if you visit this website, this URL you really should note down please, you can filter here on the side for what controller you want, and then you can very easily download a documentation package which contains worked examples. Any questions so far? Okay. Then it is time to just show you a little bit how the HAL behaves. First of all, here we've got a bit of code. Who of you knows what it does? Take a guess. The hello world of embedded engineering. What do you think it is?
It's like same in Arduino, like the blink.
Exactly.
1 second on, 1 second off.
Exactly. What do we see here? Main, it's normal, it's C. Here we have a function RCU parif clock enable. This is important because the core is clock gated. And every peripheral device you want to use, you first need to connect it to the clock generator. Then you see here initialization of the GPIO. And then here we set and we clear the pins. Looks very simple. This guy here is not so much more complicated. Here we now have 2 GPIO pins, 1 input and 1 output, and then we simply mirror the value from the 1 pin onto the other pin. So if the input pin goes high, the output pin will follow suit. What is interesting here? You see here the access to the GPIO registers is done purely with static constants. This GPIOB is a static constant which indicates GPIB port B, and here we write in the static value for the pin 0 to either switch it on or off. And this trend is really kept up through the entire ecosystem. You see here, for example, we are interacting with the DAC, and you also see it's completely static. It's not like with other platforms where you have a structure which you pass through. But it's basically completely static, and it's a bit of a different programming way, but I find it very sympathetic. And yes, here we see the long one, the initialization of the DAC. Again, you see every function that we call trigger disable, wave mode config, and so on, we always use these static constants. This is an important switch for you who is coming from the espressive ESP32, because on the ESP32 basically you have a structure, and this structure represents state, and then the structure, I always say, goes shopping in the Tesco mile. The structure goes, sorry, I've still got the layout in Bratislava in my mind. It goes to the vegetables, then it goes to the fruits, and so on and so on. And here it's a bit different. Okay, I've got but 1 more minute. So the last thing, please follow me on Instagram, because every Wednesday, there is a giveaway for RISC-V stuff. Every Wednesday you can win a development board, you can win some chips, you can win a book. Every Wednesday, there is something, and usually every Friday you can win some literature as well. So with this, I wanted to thank you all very, very much. It was my honor. I'll be back in about 2 hours for OpenSCAD, 3D modeling for the creatively challenged by programming. With that, I thank you very much, and we are ready for questions, if there are any.
Does anyone have a question? Yeah?
It's not like a question, maybe just a thought experiment in my head. So basically you said there are many flavors of RISC-V, and in my experience that makes the market fragmented, which may be a bad thing, and it may be a good thing, but in reality, I think it holds back the whole RISC-V to becoming more and more popular. What do you think about this?
This is a very, very good question. He is speaking about fragmentation. My answer to this is the same answer I always gave to people when they were asking about fragmentation in the iOS market and in the Android market. Look, take a look. When you travel home today, look in the arrivals in the first class lounge, look at the people. You will see tall girls, you will see little girls, you will see fat girls, you will see skinny girls. And you will see girls with 6 fingers maybe even if there is one, sometimes. The world is full of individuals. And in a way, fragmentation, as annoying as it is, it also allows to tailor-make the individual chip to the individual needs. For example, if you have a simple control application, why do you want to carry around the silicon budget for a CAM transceiver, for an I3 receiver, all this kind of madness? I understand where you are coming from, and it is indeed an issue. But I think it's both-sided. I hope that this has answered it a little bit. Then I will give back to our moderator.
Thank you.
Any more questions?
Yeah, any more question? So, as I see, we don't have any question also from online. So, thank you, Tam, and we will be back with your OpenSCAD presentation later. Thank you.
Mariana, thank you very much.